Hey, this is Robert Quimby, and I'm going to tell you how you can take your FITS data obtained in different filters and combine them into one beautiful color image. So to accomplish this, first we have to know a little bit how your eyes work, and this will be important because we're going to replicate this process of what your eyes see. And after we've done that, then we're going to learn how we can take our data, which are going to be scaled into these 16-bit typically FITS images, and how we can rescale that down to 8 bits, which is what you want for something that you're going to look at on a computer screen. Once we've done this, we're going to take our 3 different images from 3 different filters, we're going to combine them together and put them into one data cube, one 3-dimensional array, and then we're going to use that to view our beautiful image. So we're going to start with a little bit of the basics on how the human eye works. So of course this is a very simplified diagram here. We have light entering here. This is a cutaway of your eye. So light entering here through the cornea, going through the hole here, the pupil. It gets focused by this lens here onto this back wall of the eye, the retina. And this retina is made up of all these different types of cells. There's rods and cones. And what happens is when light comes in, it actually reacts at the back of your eye, all the way in the back of the retina, with these cones or these rods, and it produces a chemical reaction which makes electricity, makes a chemical signature at least, that gets transferred into your brain through the optic nerve. And then your eye actually processes this and creates an image. So really you see with your brain, not really with your eyes, but your eye is the first detector here. So we just need to understand how this detector works. So the important thing to note is that there are different types of cells that are receiving these photons, and they have different sensitivities to different wavelengths of light. So just broadly, as demonstrated by these colors here, there are some cells that are sensitive to green light, some that are sensitive to red, and some that are more sensitive to blue light. So here actually the transmission functions for those cells. So this is a scale here in wavelength in nanometers. So this is your violets and your blues all the way out to your reds here that your eye can see. And this is giving a normalized kind of probability of absorbing one of those photons. So what this is telling you is that if you have light that comes in, say at 420 nanometers, there's a good probability that your blue cones are going to absorb that and transform it into a signal for your brain. There's a much lower probability that the green and red cones will do that, or that your rods will sense it, but it's non-zero. Keep that in mind. So what happens is when a photon comes in at this wavelength, your brain says, well, I'm getting maybe not just one photon, but let's say you're getting hundreds of photons. And a lot of those will be transformed into signals on your blue cones. Not many will be transformed into a signal on your red and green cones. And so your brain will say, you know what, this is a blue object. Same thing happens out here. Longer wavelengths, if you have light coming in at 530 nanometers, your eye is going to get more signal on the green cones than the red and the blue, so it's going to interpret that as a green object. And if you get something around 560 or longer, you're going to get more in what are called the red cones, and you'll notice this is actually kind of in the yellow territory here, but we're going to call it red cones anyways. And so your eye will determine that it's either a yellow or a red object. All right, so you can just see that by putting in photons at different wavelengths, you have different probabilities of detecting them, and your eye is just using these ratios for how many counts are received by your blue cones versus your red cones or your green cones to decide on what the color is. A couple important things to note. One is that you do have this fourth set of cells, these rods. These are not typically used in daylight conditions because they become saturated, and so they're actually not providing much signal. These are the cells that you use in low light conditions. So when you are observing, for example, and you're out in the nighttime sky and you're looking up at the sky at night, it's your rods that are sensitive. And there's only one set of rods. They don't come in different colors, and that's why we can't really see colors that well at night. Also, you'll notice that these rods are not very sensitive to red light. So if you have kind of a 6500 angstrom light or longer, you actually can detect it with your cones, your red cones in particular, but you're not going to see it with your rods. So this is why at observatories we use red lights. So we have red lights that are turned on, and this preserves your night vision, which is done with your rods. Your rods are not affected by that. They don't get saturated by red light. But you can still see because you have all these red cones that are sensitive to the light. One more thing that's important to note is that your cells, your cones and your rods, they're not spectrometers. They're only sensing, did I get a photon, yes or no. They're not telling you what the wavelength is. So if you put in light and it's absorbed in a blue cone and it's 4,000 angstrom light or 43,000 angstrom or even 5,000 angstrom light, you're going to get just a detection in your blue cones here. That's all your brain's going to know. It just says, I got a detection by this one. And it's using those ratios between your green and red and blue cones to actually determine approximately what that color is. But it can be fooled. So all you have to do is just pick one wavelength for each one of these cones and just show that light and vary the intensity of that, and you can reproduce any color. So if you say you wanted to reproduce cyan light, for example, well, you just give it, make sure that there's a similar number of blue and green photons received and maybe a little bit less of the red, and your eye will interpret that as being cyan. It doesn't matter if the light is actually cyan, actually at this wavelength. It could be at this wavelength, and this wavelength, and that'll be the same as in just a set of photons at this one wavelength. So that's important for how we perceive color. So this also points to a way that we can say fool the eye, and that is how computers actually display images. They're not showing you light at different wavelengths. They're just showing you light at 3 specific wavelengths, but they're varying the ratios of those intensities to fool your eye into seeing different colors. So here's a picture on the screen here of an eye, and if you get up close, you'll notice that this picture is made up of tiny pixels here. Now I can zoom in here and give you a close-up view so we can see this a little more clear, but each one of these pixels, you'll notice, is divided into 1, 2, 3 different bands. There's a red, a green, and a blue, and you'll see that repeated: red, green, blue, all the way across here. So this is the array that we have. We have pixels with 3 different colors in them, and just by, again, weighting the intensities of these 3 colors, we can reproduce any light you want. So if you turn all these on full blast, you're going to get something that looks white to our eye. If you turn them all off, you're going to get something that looks black. And then by varying the ratios, you can pick whatever color you want. You can make it red, you can make it brown, you can make it orange, whatever you want. So now getting to the point at hand, let's say we have data that we've taken, and we're using a telescope, and our telescope is just taking images in a single filter at a time. So we're just collecting, say, red light or just blue light. We're not getting all of the whole spectrum at one go. That's what the filters do. They block out other parts of the spectrum. But if we take 3 different images in 3 different filters, we can combine those to make a 3-color image. All we have to do is take one image, and we can use whatever filter we want, but if you want it to represent true colors, you might want to pick filters that are similar to your eye's responses. So here we can use, say, the Johnson B band, the V band, and the R band, and we can use those as proxies for your cone photoreceptors, the transmission functions of the blue, green, and red cones. So these Johnson filters are not the same as our cones, but we're just going to use them as a stand-in. So we can take that data we have, and usually those data come in 16-bit format. What that means is that each pixel can be a number between 0 and over 65,000. When we look at images on a screen, each pixel in each one of those colors, red, green, and blue, needs to have a number that's between 0 and 255. That's 8-bit. So the first thing we have to do is we have to take this data that we have that has a huge dynamic range, and we have to rescale it into a smaller dynamic range. So instead of 0 to 65,000, it's got to be 0 to 255. So there's a scaling factor here. So we're going to calculate that, and we have to do that for each one of these bands. And then once we've done that, we can combine all 3 of those 8-bit images into a single data cube, and that's what we can use, we can pass on to our computer to display as a color image. So to do this process, first thing we need to do, of course, is we need to take some data. So we've done this. Here's some data that we're taking some time ago, and these data are available if you want to go to Sirius. You can download these yourself. But these were taken in 2017 on September 28th, and I've processed these images. So that's important. We've already removed the bias and done the flat fielding, and it's also important to actually register the images, which means align them so that each pixel on each frame represents the same Aryan deck on the sky. So that's all been done here, and I have these 3 exposures that we took, exposure number 83, 84, and 85, and these happen to have been taken with the Johnson R band V band, and B band, and so we're going to use this to represent red, green, and blue light. So we'll set that. And what we're going to do first is just take a look at these images in DS9 as normal. So I'm just going to loop through each one of these exposure numbers, and I'm going to create a new frame for each one of those. I'm going to display the image and just set the scale to Z-scale and zoom to fit. So I can do this. I've already got a DS9 session open, so that's running in the back here. And if I pop that open, you can see here is one of our images. So here's now, should be the, let's see. There's the R band image, here's the V band image, and here is the B band image. And you'll notice if you kind of toggle between these, the stars, the intensities change a little bit, but there's some very obvious differences in the shape of this object here. This is a planetary nebula, and each one of these bands, of course, has a different amount of light in each of these bands in different locations because the color of this object changes with position. So that's what we're seeing here, that there's more red light here because this R band light is brighter on the top here than it is in, say, the G band, the green, or the B band, the blue. So this object is red on the edges here, and it's a different color in different other places. So what we want to do now is we want to take those images, that's the data we got off the detector, processed, and it's in 16-bit format, and we want to convert it to 8-bit. So we're going to write a little function here called get8bit, which is going to do that for us. So we're going to give it an exposure number. It's going to load the data. So it's going to use, figure out what the file name is. It's going to combine where the data are and the exposure number and the file format. And then we're going to load this using fits get data. And so we'll have our image data loaded here. And then what we need to do is we need to figure out how we're going to do this rescaling. Because right now we have pixels that are ranging from anywhere from 0 to 65,000. You can actually see what the scale is here. So we've already done kind of this job has been done for us by DS9. So you can see that the darker colors have a value of 260, whereas the brighter colors have values of around 400 or above. Right? And that's why this is all washed out here. We can adjust that. If we go to the scale parameters, we can change the scaling, and we can change that maximum value. So instead of having white be at 400, we can make it, say, 4,000-ish. And that changes what we see on the screen there. So I'll set it at maybe a little bit lower value. You can see by changing this high value here, we can see more detail inside the nebula. So this is important to know. This is what we're going to do. We're going to pick those two numbers. What do you want to call black and what do you want to call white? Anything below what we call black will be black, and anything above what we call white will be white. And then in between we'll have grayscales. So the way we're going to do this, you can just pick any two numbers, but we're going to do this in kind of a systematic way. We're just going to base the scaling off of the background. So the first thing we need to do is get a representative sample of our background pixels. So what we're going to use is we're going to use an AstroPy stats. There's this handy function sigma clip, and that'll do sigma clipping, so it'll remove outliers. And we're going to assume that the background values are Gaussian distributed, so anything that's a star will be an outlier in this distribution. And we'll just do this rejecting, because most of the pixels, as you see in the image, most of the pixels are background pixels. There's only a few, relative few pixels that are actually affected by object light. So by doing this rejection, we can get an idea of what the background level is, the background population is. So we're going to use sigma clip, and we're going to pass it this image and let that run. And then after this has given us our sample back, we can calculate what the mean is of that. Take the mean, and we can calculate what the standard deviation is of just the background pixels. And you can set DDOF equals 1 if you really want to be careful, but it's not too critical since we have such a large sample. So now we had to pick our two values. These are the level for black and the value for white. So these are in our original data units. So what we're going to do is we're going to say that we'll take this background mean, the average value of the background, and we're going to subtract off one standard deviation. And anything that is darker than that, has a smaller value than that, we're going to represent with a black pixel. And then we're going to set our white value. So again, we're going to take the background mean. And then we can pick anything that is, say, 6 standard deviations higher than the mean, and we'll make that a white pixel. and then everything in between will be grayscale. Just to make this function a little more general, we can take these values here and we can use these keyword parameters smin and smax just to set how we want to do this. So we can actually just add smin times the background standard deviation and smax times the background standard deviation. And I use -1 and 8 here, not 6, but same idea. Okay, so we've decided what's going to be white, what's going to be black, what's going to be grayscale. And now all we have to do is rescale, do the actual rescaling. Now there is a function built into SciPy Mish called toImage that does this, and there's another helpful function called byte scale that you might look up. But we're going to just do this by hand here. So here's what we're going to do. We're going to take all of our image values, and we're going to subtract off the minimum value, right? So that defines where our 0 level is going to be, okay? Now, we got to rescale this, so that's a number between 0 and 255. So the next thing we're going to do is we're going to divide by the dynamic range. So that dynamic range is just the maximum value that we care about, Cmax, minus the Cmin. Right? So this is now going to take everything in the image, set it to our Cmin value to 0, and then at the Cmax value, since we did this division, that's now going to be equal to 1. So we're going to have numbers between 0 and 1, but we're still going to have numbers that are less than 0 and greater than 1, but the numbers between 0 and 1 are the ones that we're going to have in our grayscale. And we're going to have 255 colors, right? 256, we're not counting 0, right? And then one more thing we need to do is we're going to make these into integers, so we're going to first round this, just use numpy round, and round that whole thing. And now we're going to have rounded numbers. They're not all going to be between 0 and 1, or 0 and 255 now, just the ones we care about. So the ones that are less than 0, we're just going to set those to 0. And the ones that are greater than 255, we're going to set those to 255. So now we have our 256 values for our scaled image. We're going to tell NumPy now that we want to treat this as a 8-bit array. So we're going to convert it from that floating point numbers to our 8-bit floating point, 8-bit integers now. And that's our final value, and we're just going to return that from this function. So that's it. So now we can go ahead and we can use this. We can use our get 8-bit function. We'll pass each one of those exposures that we care about. I've set this smax value to a higher value just to pull up the contrast a little bit more. But we can run this cell, and now we have arrays called R, G, and B representing our red, green, and blue light. So then the next thing to do is to combine these. So what we need to do now is we need to make a data cube. So we're going to use numpy zeros, right? And we're going to build a 3-dimensional array. So first we're going to take the shape of our data. So we just take the R, that's our array that we just made, and find its shape. It's going to find NX, NY, and NX. And we're going to make sure that our output image, IM, is going to have those same dimensions. But it also needs a third dimension, which is the channel number. And we're going to have 3 channels, red, green, and blue. And this whole thing, again, is going to be an unsigned integer. So we're going to tell NumPy to make it integers, 8-bit integers. So once we've done that, then we can populate this image with each one of our channels. So we'll take this image, and for every pixel in the 0th channel, we're just going to use the values in R. And then we can do the same thing for the other 2 channels. So I'll just copy and paste this. So everything in the first channel and the second channel, oops, we want this to be green and blue. And remember, it's always RGB, red, green, blue. That's the order. Make sure you remember RGB. So once we have populated our array, we can just pass this now to imshow. This is just a matplotlib function imshow. And when you give imshow a 3-dimensional array that happens to be 8-bit, it's going to interpret that as a color image, and it's going to use the computer's standard processing tools to show it for you. So we can do this, and there it is. There's our beautiful 3-color image that we just made. So the last thing you might want to do is you might want to save this. You might want to put this on the disk somewhere. And you can use this using using a package called PIL. This is the Python image library, and this has all the handy tools you need for reading and writing things like PNGs or JPEGs or GIFs or whatever you want to do. So we're going to use the image object, and there's a from array function in there. So we'll pass it our 3-color image, and then this is just the data cube, the 3-dimensional data cube, and it's going to create us an object here, and then we'll use the save function from that object, and this happens to be M27, and we'll tell it the file name that we want it to output as, and it'll look at the extension here .png, and it'll decide what type of image to make. So if I change this to GIF, it'll make a GIF, but if I want PNG, which is a good format, we can do that, and that's that. It saves it to disk. Now, one last thing to note, there is actually a way to do this all with DS9 if you're interested. You can follow this link if you want to get explicit details on how to go through and create all this. I'll just give you a quick overview here. The basic idea is that you got to first create an RGB frame. So you create this frame. I'll just run this cell here, and you see this little window pops up here. And what this is showing you that now you have one frame that can have 3 different images, a red, a green, and a blue image. And then all you have to do is just load in different images into this frame, into each one of these channels in this single frame here, and it'll make the color image for you. So I've got a little script here that'll do that for you. It's going to create a red, a green, and a blue channel, and it's going to use our exposures, and just like before, it's going to take that RGB frame in, say, red first. So it's going to set to RGB red. Then we'll be able to adjust the file in there. So we'll change the file in the red channel to the first exposure, change it to Z-scale and zoom to fit, and then the same thing for green and blue. And when you execute this, you can see what it does is it creates this 3-color image. Now you might notice that the contrast here is not what you may want. You can go back and actually edit this as we've done before. So right now we're on the blue channel. So if we go to scale parameters and we change the low and the high values here, this will only affect the blue channel, not the other two. So if I pull this out here, you can see that it makes it a weird color because it turned down the blue, right? Now if I go to the red and I do that same thing, it'll just affect the red, and then I can go to green and also change the scale on green. And there we have it. So you have to be careful with how you do this so that you make an image that is either scientifically valid or that reproduces the colors well. I think I got it turned, maybe I'll turn the red down a little bit more, because I think it's a little too red. There you go. And now you can see that we've made a very high contrast image here. So we've turned down the values, but actually now you can see this the central object here, and you can notice it even looks blue, and it should, because that's a white dwarf star, which is a blue object. So that's the white dwarf in the center of this planetary nebula. So there's a couple ways that you can make color images. So go ahead and play around with this and enjoy.